Hello friends, IBM is here with episode 4 of electricity and DC circuits. Today we shall not waste much time, let's just move to episode 4. Do not forget, if you are new to this channel, the documents are attached, the links to the documents are attached in the video description. Click on them to open the documents and download, then print and follow with the hard copy. So we move to the document. I think in episode 3 we stopped around here and my pen jammed. I hope it is now doing well. So number 2033, a metal electrical conductor has a resistance of 5 kilo ohms. The potential difference of 9 volts is applied across its ends. How many electrons? I'll use capital N for number of electrons. Pass a point in the conductor in 1 minute. So the time is 1 minute. Okay, so we know that current flowing through a conductor is going to be given by total charge divided by time. And this is given by a number of electrons times the charge of each electron divided by the time t. But they gave us the PD and we have the resistance. So the current is also going to be equal to the PD divided by the resistance from V is equal to IR. Therefore, I'll just ignore this part of the equation and concentrate on the other end. So number of electrons, number of charges is going to be equal to V, which is 9, times T, which is, I'm just cross multiplying here, times T the other side, which is 1 minute, that is 60 seconds, divided by R, which is 5.6 times 10 power 3, divided by E, which is the charge of one electron, 1.6 times 10 power negative 19. So this is going to be 9 times 60 divided by 5.6 exponent. Okay, I'll open another bracket, two brackets, 5.6 exponent 3 times 1.6 exponent negative 19. Close the brackets. So this is giving me 6.0 times 10 power 17. So which makes the answer to be C. A battery of e.m.f 12 volts and negligible internal resistance is connected to 3 resistors, each of resistance is 6 ohms as shown in the figure here. What is the power dissipated in resistor R? Power dissipated in resistor R. So we know that power is equal to I squared R. Power is I squared times R. And the I is equal to the EMF divided by total resistance, which is R total. So the EMF is 12. Total resistance, let's find total resistance. These ones are in parallel. The total here is going to be 3 ohms. That is 6 times 6 over 6 plus 6, which gives us 3. Or 36 over 9, over 12, which is 3. Which is just a half of the resistance of just 1. Then 3 plus 6 gives us 9. So that is 12 over 9. That is the current. Or this can be 4 over 3. And then therefore power is going to be 4 over 3, and this is squared, then times R, which is going to be 6. So this is going to give us a 4 over 3 squared, then times 6, which gives us 10.66 recurring, which is actually 10.7 or 11. So this is approximately 11 watts. So the answer is going to be C. The box containing 2 electrical components connected into a circuit. The variable resistor is adjusted and measurements are taken to determine the IV characteristic for the box as shown in the figure. Okay. So which arrangement of the 2 electrical components in the box will create the best fit to the measured IV characteristic? Best fit the measured IV characteristic. So this can't be a filament. It can't be a filament lamp because okay, so that the resistance increases, of course, later on, but it seems we can actually not consider a filament lamp. Here A is saying a filament lamp and a fixed resistor in parallel. So a filament lamp and a fixed resistor in parallel. So let's first go back to the setup. So a box containing two electrical components is connected into a circuit. The variable resistor is adjusted and measurements are taken to determine the IV characteristic for the box. So we are seeing that when the variable resistance is adjusted, the graph is showing that as the PD increases, the current increases, and then with the time the resistance increases. So with the time the resistance increases. That means if the resistance increases, that means the filament lamp should be involved here if the resistance with the time increases. Therefore, the combination should have a filament lamp. But then, because there are two components, so the combination should have a filament lamp. And all of them have a filament lamp. But then, if it is in series, let's first establish whether it will be in series or in parallel with a fixed resistor. So if the filament lamp, anyway, if the filament lamp and let's say we have a filament lamp and it has two electrical components. Let the other one be maybe a resistor, because let me see, we have, I think, resistors. We have a filament lamp and fixed resistor, filament lamp and fixed resistor. If it is a filament lamp and a fixed resistor, if it is a filament lamp and a fixed resistor, it means we shall not have any point where the voltage, the PD is going to be 0. And if it is a filament lamp, okay, if it is a filament lamp and a resistor, then this part here is really not going to be making sense. It is not going to be making any good sense if it is a filament lamp. Therefore, we shall ignore A. We shall ignore wherever we say resistor. There is a filament lamp but a fixed resistor. It means there will be always a PD across the fixed resistor as long as there is a current flowing. Therefore, the fixed resistor will be left out. Then let's look at the filament lamp and the semiconductor diode. If they are joined in parallel, it means the PD across them will always be the same. If they are joined in parallel, the PD across them will be always the same. Therefore, there will be no point where the resistance will be increasing with time. But if they are joined in series, the current flowing through them is going to be the same. That means if the temperature of the filament increases, then the resistance is going to actually decrease. Therefore, this is most likely going to be a semiconductor. Remember, for a semiconductor, the IV characteristic is supposed to be like this. It's supposed to be like that. And yet for a filament lamp, the IV characteristic is supposed to be like this. For a filament lamp. So it's like if these two are put in series, that's when we shall have this as the resultant. But if they are put in parallel, we cannot have this as the resultant, because in parallel, of course, total resistance becomes smaller even when that means the current flowing as the PD increases. Since they're in parallel, if resistance of one increases, total resistance is actually going to be smaller. Yet here we are seeing total resistance is becoming greater because the change in current is reducing. Therefore, our answer remains D. A cell of internal resistance 0.5 ohms is connected to a fixed resistor of resistance 10 ohms. The resistance of the resistor is changed to 20. Which statement is not correct? So we have a cell, we have initially 10 ohms joined to a cell with internal resistance. The internal resistance is small r is 0.5. Let this be connected to a battery. And then for the second case, we repeat the same. And I don't need the second battery. So let this be 20 ohms. Remember, this is 0.5 internal resistance. This is 10 ohms. So which statement is not correct? Note that the resistance has been increased, so the current must be decreased. Is the current halved? Let's check. We know that e.m.f is equal to I over R plus small r, so the current is equal to the e.m.f divided by R plus small r. We notice that small r has remained constant. The e.m.f is remaining constant. It's only capital R which has been doubled. So capital R has been doubled, but this does not mean that it is, because this is plus, doesn't mean that this has been halved, even though the R is in the denominator. So this one is going to be wrong. The e.m.f of the cell will remain constant. I think that is true. The e.m.f of the cell remains constant. The power dissipated by the fixed resistor will decrease. Power in the fixed resistor will decrease. Of course, power is equal to I squared times R. R has been doubled, but I decreases, and since it is squared, then the power dissipated also decreases. Because I is squared, the power dissipated decreases. The other one is just doubled, but I is squared. Then the terminal PD of the cell will increase. The current flowing is decreased. The lost volts is decreased. That means the terminal PD is increased. So the terminal PD is increased. This is also true. So these ones are true. And therefore, it means the one which is not correct is A. The current in the circuit will have. That is not true, because current is inversely proportional to the total resistance, not only to the fixed resistor. In the circuit shown, all the resistors are identical. All the resistors are identical. The reading V1 is 80 volts. So here we have 8 volts. The reading V2 is 1 volt. So this is 1 volt. But remember, the resistors are identical. This is R, this is R, and these ones are in series. So the current here is the same current here. So if the current is the same, V is equal to I times R. The resistance is the same, the current is the same, it means the PD here is also going to be 1 volt. Because they are identical and the current through them is the same, the PD across them is going to be the same. Okay? So that means the reading of V4 is actually reading the PD across this, which is 1 plus 1, which is equal to 2 volts. So V4 is reading 2 volts. That means our answer is going to be B without even wasting any time. We can check V3. So if V4 reads 2 volts, and this resistor here is identical to this one here, they are identical and the current is the same. So the PD here is the same as the PD here. So twice V3, because this is also V3. Twice V3 is going to be 8 minus 2, minus the PD across this parallel combination. So that means V3 is going to be equal to 6 divided by 2, which gives us 3 volts. So that is B. The diagram shows a simple circuit. Yeah, it is very simple. Which statement is correct? When switch S is closed, the e.m.f of the battery falls because work is done against the internal resistance. The e.m.f of the battery is constant. When the switch S is closed, the EMF of the battery falls. The EMF is constant. When switch S is closed, the potential difference across the battery falls because work is done against the internal resistance. That is very true. If the potential difference, the terminal PD across the battery falls, that is the terminal PD falls, it's because work is done against the internal resistance. When switch S is closed, the potential difference across the battery falls because work is done against the resistance R, not at all. Here it is only because there could be lost volts within the cell. That's why the PD across R falls or reduces. A resistor has resistance R. When a PD across the resistor is V, the current in the resistor is I. The power dissipated in the resistor is P. Work is done when charge Q flows through the resistor. What is not a valid relationship between these variables? Okay, let's check this very well. So this one is P is equal to IV. I think that is valid. This one, potential difference is work done per unit charge. That is valid. Power is equal to I squared R. That is valid. Now this one, power is supposed to be V squared over R, not V over R. So this one is not valid. So the answer is D. A wire of resistance 9.55 ohms has a diameter of 0.28 millimeters. It is made of metal resistivity 4.9 times 10 power negative 7 ohm meters. What is the length of the wire? So we know that resistance is equal to rho L over cross-section area. So it means the length is going to be R times A over resistivity. So we substitute. R is 9.55 times cross-section area. Remember, area is equal to pi d squared over 4. So this is going to be pi times d, which is 0.28 times 10 power negative 3. And this is squared. Divide by 4. So we shall have 4 times rho, which is 4.9 times 10 power negative 7. So 9.55 times pi times 0.28 exponent negative 3, and this is squared. That is divided by 4 times 4.9 exponent negative 7. So that is giving us 1.2. So this is 1.2 meters, making the answer to be A. Charge carriers, each of charge Q, move along a wire of fixed length. The number density of the charge carriers in the wire is N. What is also required for the wire to determine the average drift velocity? So we know average drift velocity is equal to never. Never, instead of E, I'll put Q, V times A. So they have mentioned N, they've mentioned Q. So N and Q have been mentioned, and we want to find the average drift velocity. So we need the area and maybe the current. So NQ, or say V is equal to N is equal to the current over A times NQ. Okay, so current per unit cross-sectional area, I think that is I over A, which is the only thing missing, so the answer is A. We may not need the potential difference, resistivity, and length. A potential divider circuit is constructed with one variable resistor X and one fixed resistor Y, as shown here. The potential difference across X is Vx, and that across Y is Vy. As the resistance of X is increased, what happens to Vx and Vy? resistance of X is increased. So if resistance of X is increased because they're in series, it means PD across X is going to be increased. Because EMF is equal to the PD across X, EMF is going to be PD across X plus PD across Y. When this one increases and this one is constant, it means this one must decrease. Therefore, it means PD across X rises, the PD across X raises, so this is wrong, and it means the PD across Y falls, so the answer is going to be C. A cell of EMF E and negligible internal resistance is connected into a circuit as shown here. The voltmeter has a very high resistance and reads a potential difference V out. So because it has a very high resistance, that means there is no current going through the voltmeter. Therefore, we shall just choose currents. Let's say this is I, this is say I1, and this is say I2. I will put here a loop, which is clockwise. So using that loop, we have EMF. I'm using Kirchhoff's second law. Sum of EMFs, there's only one cell, so it is E. Sum of potential drops will be I1 times 12, so it is 12 I1. Then putting a loop here, I can put this loop in, let me put the loop downwards and clockwise. There is no cell here, so the EMF is 0. And the sum of PDs moving anti-clockwise. So this one, maybe let me call this one, because no current takes this route. The current here is the same current here, so this is going to be I2. Okay, so moving around that loop, I have 4 times I2, then that is negative because it's the other way around, then minus 2 times I2, then plus 12 times I1, but remember 12 I1 is E. So I will have that 0 is equal to, this is negative 6 I2 plus E. So in other words, I can say that I2 is equal to E divided by 6. That is I2. Okay, now let's find the ratio. But V out is the PD across 4 ohms. V out is the PD across 4 ohms. Using Ohm's law, V out is going to be the current, which is now I2. The current here is I2, then times the resistance, which is 4 ohms. So this is going to be E over 6 times 4, which is precisely 2 over 3 times E. That is V out. Now let's find the ratio. So the ratio is going to be 2E over 3 divided by E, which gives us 2 over 3 automatically. So our answer is 2 over 3. So the ratio was equal to 2 over 3 E over E, which is giving us 2 over 3. 5 resistors are connected as shown in the figure. What is the total resistance between points P and Q? What is the total resistance between points P and Q? That is very easy. These ones are in series, we add, so they give us 28. These ones are in series, we add, they give us 14. So we now have all these ones in parallel. So total resistance, 1 over total resistance is going to be 1 over 28 plus 1 over 14 plus 1 over 7. Remember to find the reciprocal at the end. So I'll just put this in the calculator. 1 divided by, that one delays me a lot. 1 divided by 28 plus 1 divided by 14 plus 1 divided by 7. Then I get the reciprocal because, so it means 1 over R total is equal to 1 over 4. Then I get the reciprocal. So R total is going to be equal to 4. So our answer is C. The current I in a metal wire is given by that expression. What does N represent? N is number of free charge carriers per unit volume, or the charge density, the number density of charge carriers. So number of free electrons per unit volume, our answer is C. The circuit diagrams show two lamps X and Y, each connected to a cell. The current in lamp X is 0.5 and its resistance is 9.6. The current in lamp Y is 3.0 and its resistance is 1.2. What is the ratio of power in X over power in Y? So that is very easy. Power is equal to I squared R, so we can find the ratio directly. The ratio is equal to, for X, that is 0.5 squared times resistance 9.6. For Y, it is 3 squared times 1.2. 0.5 squared times 9.6 divided by 3 squared times 1.2. So that is 2 over 9, which is 0.2 recurring. So the answer is going to be A. A cylindrical piece of a soft electrically conducting material has resistance R. It is rolled out so that its length is doubled, but its volume stays constant. Length is doubled, volume remains constant. What is its new resistance? Okay, so this is very easy. We note that our resistance C is equal to rho L over cross-sectional area. Remember the resistance, the volume is staying the same, so I have to look for volume. And note that volume is equal to cross-sectional area times length. So volume for the first one, I'll call it V1, is going to be L times L. And volume for the second one, I'm calling it V2. The area is not known, so let it be A2. But the length is twice, so this is twice L. Of course, if the volume is twice, the area is supposed to be a half. So that means if the volume is twice, because they are supposed to be equal, so I can say A2 into twice L is equal to A into L. So it means A2 is going to be equal to a half. That is a half of A. Okay. So what is its new resistance? So the new area is going to be a half A. So I'll just substitute here. So the resistance is going to be rho. I hope it is the same material. A cylindrical piece of soft electrically conducting material has a resistance R. It is rolled out, so it is the same material. So this is going to be rho times L. Where there is area, I'm going to put a half A. So this is a half A. So you notice that this becomes, so a half A, it is not a half of 1 over 2A, it is a half A. So since it is a half A, the 2 goes up, it becomes twice rho L divided by A, but rho L over A is R, so this becomes simply twice. It simply becomes, is it twice or 4 times? No. L area is a half A, length is double. The area is a half A, length is double, so I didn't put length there, so let me put length there. If I substitute in the same formula to find a new resistance, which I'm calling R2, it will be rho. Where there is L, I have to put there twice L. Where there is A, I have to put there a half A. So this is twice L times 2, which becomes 4 rho L over A. And that means it is 4 times R. So it is 4 times R. Therefore, our answer is going to be D. The sum of the electrical currents into a point in a circuit is equal to the sum of the currents out of the point. That is Kirchhoff's first law. Which statement is correct? This is Kirchhoff's first law, so this is not second law, of course. It is Kirchhoff's first law and is a conservation of charge, so our answer is automatically A. In the circuit shown, the batteries have negligible internal resistance. What are the values of the currents I1, I2, and I3? So here we shall just use Kirchhoff's laws. What are the values of the current? So number one, at the junction, you will notice that I2 is leaving, I3 is entering, I1 is entering. So I'll simply say that I2 is equal to I1 plus I3. The sum of currents into a junction is equal to the sum of currents out of the junction. Then I'll choose the loops. Let's have this loop here, which is clockwise. One of my students suggests that when the loops are always in the same direction, the algebra becomes easy, but me, I will choose loops in opposite directions. Okay, so using these loops, using the first loop, there's only one cell of 15 volts and it is positive EMF because the loop is in the same direction, negative, positive, and the loop is in that direction. So it means we are moving in the right direction of current from this battery. So that means the EMF is positive. Then sum of PDs. Here we have 2 times I1 and here we have plus 2 times I2. Okay, so this means I can put this equation into this one. I'll put that equation into that one. So which one should I remove? Let me remove I2. Okay, let me remove I2. But before I remove I2, let me look at the second loop. The second loop, the EMF is going to be 9, positive 9. The PDs, we have this current is in the same direction as the loop, so this is positive. So that is 2 times I2. And this current is in the same direction also as the loop. So this is also going to be plus 2 times I3. So because here I have I2 and I3, I'm automatically going to eliminate I1 in the first equation here. So when I remove in that equation, I have that 15 is equal to 2 into where there is I1, I'm putting I2 minus I3. I2 minus I3 plus twice I2. I'm simplifying it further. I have 15 equals to twice I2 plus 2I2. That becomes 4I2 minus 2 times I3, which is twice I3. Okay, so I'm combining that equation with 9 equals to 2I2 plus 2I3. Let's add these equations. So we are adding. When we add, we get 14 equals to 6I2 plus 0. The other one is 0. So it means I2 is going to be 14 divided by 6. I2 is going to be 14. Is it 14? 24. 9 plus 15, that is 24. So it is 24 divided by 6, which is actually going to be equal to 4 amperes. So I2 is 4 amperes. So if I2 is 4 amperes, it means I've eliminated this one and that one. So A is out and D is out. Then I can try to find, I'm going to try to find maybe, let me try to find I1. Oh, I find I3. Let me find I3 then. So taking back I2 into that equation, so I'll have that 9 is equal to 2 into I2, which is 24 over 6 plus 2 I3. So I2 is 24 over 6 is automatically 4. Let me not waste much time. So this is 4. So you have 9 minus 8, that is 1. is equal to twice I3, which means I3 is 1 over 2, which is 0.5. I3 should be 0.5, which is this. So our answer is going to be C. Our correct answer is C. A battery of EMF 6 volts and negligible internal resistance is connected to 3 resistors as shown in the diagram. Each resistor has resistance of 4 kilo ohms. What is the current in resistor X? So we want the current in resistor X. First of all, we can find total current in the circuit. Total current is equal to EMF divided by total resistance. These, remember, are in parallel. When I combine them, I am very sure I will get 2 kilo ohms because resistors in parallel, if they are only 2, you can simply get the product over the sum. So it is 4 times 4 over 4 plus 4, which gives us 2 kilo ohms. So total resistance is going to be 2 plus 4, which is 6. So the EMF is 6 divided by total resistance, which is 6,000. I think this gives us 1 times 10 power negative 3 amperes or 1 milliampere. So 1 milliampere enters this junction, and since the resistors are identical, the 1 milliampere divides equally. So it means the current through X is going to be 1 divided by 2, which is going to be 0.5 milliamperes. The 1 milliampere is the current here, 1 milliampere. When it reaches the junction, it divides, part takes that, and part of it takes that row. But because these resistors are equal, it divides equally. That's why I'm taking the answer to be B. A uniform resistance wire XY of length 100 centimeters is connected in series with a cell L. Another cell M is connected in series with the resistors of resistance 5, 10, and 15. The PD between P and Q is balanced against 12.5 centimeters. And remember, the PD across P and Q is the same as the PD across that length because PD is directly proportional to length. So it means 5 ohms is balanced by 12.5 centimeters. The PD across the resistor is then balanced against other lengths of the resistance wire. Which balanced lengths of resistance wire correspond to the connection points given in the table? So we have Q and R. Q and R, this is 10 ohms. Say 5 ohms corresponds to 12.5. 10 ohms is twice of 5, so it means 10 ohms is going to correspond to 2 times 12.5, which is equal to 25 centimeters. So 10 ohms QR should be 25. So this one is wrong. The rest it means A is out because QR is showing 12.5. Let's say check Q and S. Q and S. Q and S is 10 plus 15, which is 25. Note that 25 is equal to 5 times of 5 ohms. And remember, for 5 ohms, it is 12.5. So it means 25 ohms should be balanced with 5 times 12.5, which gives us 5 times 12.5, that is 62.5. So Q and S, so this is correct. Q and S, this is still correct. So B is still in, C is out, D is still in. Of course, A has already been got out. So A and C are being pulled out. So if A and C are pulled out, Q and S The balance length is 62.5, which is true. So it means our answer is going to be precisely B, because Q and R it was 25, Q and S is 62.5. We can check P and R. P and R we have 5 plus 10, which is 15. 15 is 3 times 5 ohms. So P and R would be 3 times 12.5, which I think is 37.5. 12.5 times 3, that is 37.5. So our answer is going to be B, because although these are correct, this one is not correct. A motor is required to operate at a distance of 800 meters from its power supply. So it means the length of the wire is going to be 800 here plus 800 there, giving a total length of 1,600. So the total length is 1,600. Total length is 1,600. The resistance of each of these wires is 0.05 per meter. So total resistance, if 1 meter has this resistance, so total resistance of all the length of the wire is going to be 0.005 times total length, which is 1,600. That is the total length. I think that is half of that is 8. 0.005 times 1,600, which is 8. So total resistance is 8 ohms. That is total resistance of the wires. Okay, then total PD across the wires. Total PD across the wires is going to be given by Ohm's law, I times R. The current is given as 0.6, so it is 0.6, then times 8. I think 0.6 times 8 is most like a 4.8. 0.6 times 8, that is 4.8. So PD across the wires is 4.8. That is total PD across the wires. So it means we want the minimum output PD of the power supply. So the PD of the power supply is going to be the PD through the wires, the PD across the wires, plus the PD across the motor. So this is going to be the PD across the wires is 4.8, plus the PD which is required by the motor is 16. So this should be supplying 4.8 plus 16, which I think is 20.8. So the power supply should have a PD of, the minimum output PD of the power supply should be 20.8. Which graph shows the variation of V with the I of a semiconductor diode? Remember, there is a threshold voltage for the semiconductor diode. So it starts conducting current at a certain voltage, which is approximately 0.5, 0.6. So it means we have to choose between. This one is showing there is a current for 0 voltage, that is wrong. There is a current in the negative side for 0 voltage, that is wrong. So we have to choose between D and B. But remember, a semiconductor diode is forward biased. Therefore, our answer is going to be B. The diode is forward biased. It is forward biased. So our answer is going to be B, because it will not conduct for negative values of voltage. It will not be able to conduct because it is forward biased. So the answer is going to be B. 4 different resistors are arranged as shown. A current of 1.5 amperes enters the network at junction X and leaves through junction Y. Okay. What is the current in the resistor of resistance 30 ohms? So first of all, we can find the total resistance here. This is 50 plus 30 plus 60. 50 plus 30 plus 60, that is 140. So this side we have a resistor of 140 ohms, and it is twice the other one. Remember, current is inversely proportional to resistance. When the resistance is twice, the current is half. So the total current of 1.5, if it enters here, if the current here is I, the current there is going to be twice I, because the resistance this side is twice the resistance the other side. So I'll say 2I plus I is going to be equal to 1.5. I is the current going this side. So you must have been able to notice that total sum of the resistances down here is twice the resistance up there. And then using Kirchhoff's first law, we come up with the fact that the current here, why isn't my eraser working? So the current here is, these ones I said they are giving a total of 140 ohms, which is twice this one. So it means the current here, if the current here is I, the current here should be twice I, because current is inversely proportional to resistance. So it means I is going to be 1.5 divided by 3. And they want the current through 30 ohms, which is the current through 50 and 60. So 1.5 divided by 3 should be 0.5. So this is equal to 0.5. So the answer is going to be B. A cell of constant e.m.f. A cell of constant e.m.f. or electromotive force drives a current I through an external resistor of resistance R. The terminal PD across the cell is V. When the internal resistance R of the cell increases, what is the effect on V and on I? Internal resistance increases. Remember, we say the e.m.f. of a cell is equal to the terminal PD plus the lost volts. So the terminal PdV is going to be the e.m.f, which is of course constant, minus the lost volts is current times the small internal resistance. So they have said the internal resistance increases. So internal resistance increases. So if internal resistance increases, automatically total current decreases, because the e.m.f is not going to change. Total resistance in the circuit increases. So I will say R total increases, which prompts the current to decrease. Because R total resistance of the circuit increases, so total current in the circuit decreases. So I must decrease. So we eliminate the C, we eliminate B and D. Then, if that is true, we are remaining with A and C. So what happens to V? Of course, from this expression, of course, if the current has decreased, total current in the circuit decreases. When R increases, total current in the circuit decreases. And then how about the terminal PD? Of course, the terminal PD is equal to the e.m.f minus the lost volts. The terminal PD is equal to the e.m.f minus the lost volts. As I increases, the lost volts increases, it means the terminal PD automatically decreases. Therefore, our answer is going to be A. The PD across the terminals of the battery decreases, which is the terminal PD, and the lost volts, or I mean the total current through the circuit also decreases. Okay. Alternatively, if you can look at the current has decreased because total resistance has increased, and the current, and you want V is it's like the PD across R, which is I times R, which I has decreased, means this value here has become smaller. I hope you see that. In the circuit shown, the batteries are identical and all have negligible internal resistance. All of the resistors have the same resistance. The diodes have zero resistance when conducting and infinite resistance when not conducting. Infinite resistance when not conducting. In which circuit is the current in the battery greatest? Okay, we want current to be greatest. So I want you to note that a diode is forward biased. So let's first identify where it is conducting. Here they are conducting because current is supposed to be flowing like that, the same way. So these ones they will be conducting, these ones they will conduct. So here this diode is not conducting, so the resistance here is infinity. Here this diode is not conducting because it's the other way around, the resistance here is infinity. Okay. So it means here the total resistance here is the resistance of this. If these are identical resistors, so the total resistance here is R. So the current here will be e.m.f divided by R. And then here, this diode is conducting. The diodes also have some resistance. All of the resistors have the same resistance. The diodes have zero resistance. Okay. So if the diodes have zero resistance, it implies that the current here in C is the same as the current is going to be the same as the current in D. So we cannot have two options. So these two must obviously be wrong. So let's come back here. In both cases here, the diodes are conducting, so the resistance is not infinity. So in this case, the total resistance here is going to be R divided by 2 because they're in parallel. Yet in this case, total resistance is going to be twice R because they're in series. Remember, current is equal to e.m.f over total resistance. So the question is, in which circuit is the current in the battery greatest? So since current is inversely proportional to resistance, where the resistance is smallest, the current is greatest. So our answer is going to be A, because R over 2 is smaller than twice R. So where the total resistance is smaller, the current through the battery is greatest. So the answer is A. A thermistor is an electrical component with a resistance that varies with the temperature. A thermistor T is used in a fire alarm system. The alarm is triggered when the potential difference X between X and Y is 4.5. Okay, I think that is an easy question. What is the resistance of T when the alarm is triggered? When the alarm is triggered, the PD across XY is 4.5. Okay, so how do we get PD across XY? PD across XY is supposed to be 4.5, but we are using potential dividers. This will be the resistance XY, which is 150, over total resistance, which is 150, plus resistance of the thermistor, times the voltage supply, or V in, which is equal to 12. That is from the potential divider formula. So here I just solve this. I'm just going to solve this. So I will take, I'll just check my calculator. So I have 150 times 12. I will divide this by 4.5, that is 400. So 400 is equal to 150 plus R of the thermistor. So I have 400 minus 150, which gives me 250. So resistance of the thermistor is 250 ohms, making the answer to be C. Alternatively, if this is 4.5, then this is going to be 12 minus 4.5. 12 minus 4.5, which is 7.5. So this will be 7.5. So it means if I consider the thermistor, the resistance of the thermistor is RT over total resistance, which will be RT plus 150 times the voltage supply, which is 12, should give us the PD of 7.5. That is the potential divider formula. So still, here you will just cross multiply, you get 12 RT is equal to 7.5 RT plus 150 times 7.5. That is 1125. Collect like terms. So I'll just say 12 minus 7.5. 12 minus 7.5. That is 4.5 RT is equal to 1125. Then I will divide 1125 divide by the answer. That is 250 ohms. What is a possible charge on a particle? Remember, charge is quantized. It must be a multiple. Charge is equal to N times E, where N should be a whole number. N should be a whole number. Okay, of course not 0. So let's check. We just divide this by, so it means I will just check the values of N by dividing the charge given over the elementary charge, because charge must be a multiple of the elementary charge. Already this one is smaller than the elementary charge, so I will ignore it. The elementary charge is 1.6 times 10 power negative 19 coulombs. And we are seeing that this is smaller because of the power negative 20. So I remain with the 4. 4 divided by 1.6, because the power of 10 is the same. 4 divided by 1.6, that is not a possible charge. Here the power is not the same, so I'll use the whole of it. I'll say 1.12 exponent negative 18 divide by 1.6 exponent negative 19. 7. So this one is giving us a whole number, so the answer is this. You can also check 9.11, but I'm very certain it's only this which is going to give us a whole number for N. A slice of germanium of cross-sectional area 10 centimeters squared carries a current of 556 microamperes. The number density of charge carriers in germanium is 2 times 10 power 13 centimeters, per centimeters cubed. So immediately we can change these units, of course. 1.0 centimeters squared is 1 times 10 power negative 4 in meters squared. This one will be 2 times 10 power 13 times 10 power 6 to change it to per meter cubed. If you can't see that, remember 2 times 10 power 13 per centimeter is the same as 1 over, divided by 1 centimeter cubed, which is the same as 2 times 10 power 13 divided by 1 centimeter cubed is 100 times 100 times 100 in meters cubed. But this is, actually it is 1 over 100 in meters cubed, which gives us 10 power negative 6 meters cubed. When it goes up, it becomes power positive 6 meters cubed. Okay, what is the average drift speed? Velocity of the charge. So we know that current is equal to never. So drift speed V is going to be the current divided by NEA, which is going to be 56 times 10 power negative 6 divided by 2 times 10 power 13 times 10 power 6, which would have been just times 10 power 19. Then I multiply this by 1 times 10 power negative 4, that is the area. And I multiply this by 1.6 times 10 power negative 19, which is the charge. So I'll check my calculator. Let me start by simplifying the denominator but anyway, it is not very hard. 5.56 exponent negative 6 divided by 2, I'll put 2 brackets, 2 exponent 19, that is power 13 times power 6, that is power 19. Open another bracket, 1 exponent negative 4, that was the area. Open another bracket, 1.6 exponent negative 19, close that bracket and close the bigger bracket. So that gives me 7 over 40, which is 0.175 meters per second. So our answer is going to be 0.175, that is 0.18, to two significant figures. A cell of EMF E and internal resistance R is connected to an external resistor of resistance R as shown. What is the power dissipated in the external resistor? So we know that EMF E is equal to current over into total resistance capital R plus small r, meaning the current is going to be the EMF divided by capital R plus small r. But we know that power dissipated is equal to I squared times R. So this is going to be E over R plus small r, but this should be squared times R, which is E squared over R plus small r squared times R. So our answer is going to be possibly B. The graph shows the IV characteristic of an electrical component. Of course, this is a diode because the threshold is about 0.5, 0.6 for a diode, and it is forward biased. So there is infinite resistance for negative values of V. So this is a semiconductor diode without even any hesitation. A metal wire of length 1.4 meters has a uniform cross-sectional area of 7.8 times 10 power negative 7 meters squared. The resistivity of the metal is 1.7 times 10 power negative 8 ohm meters. What is the resistance of the wire? So we know that resistance is equal to rho L over cross-sectional area. They have given us everything, it's just simple substitution. 1.7 times 10 power negative 8 times the length, which is 1.4, divided by cross-sectional area, which is 7.8 times 10 power negative 7. So this is 1.7 exponent negative 8 times 1.4 divided by 7.8 exponent negative 7. Close the bracket. That gives us a 0.0305, which is approximately 0.031. This is 0.0305, which is approximately 0.031. So our answer is B. A battery of EMF 6 volts and negligible internal resistance is connected to 3 resistors, each of resistance 6 ohms. Which circuit will produce a current through the battery of 0.67 amperes? Let's begin with the first circuit. If it gives us that current, we stop there. So these are in series, in parallel. Whenever two resistors that are identical in parallel means the total resistance is half of the resistance of one. So here it is 3 ohms. So we have 3 ohms in series with 6 ohms, giving us a total of 9 ohms. So let's find the current. Current is going to be equal to the EMF divided by total resistance, which will be the EMF is 6, total resistance is 9. So 6 divided by 9, that is 0.6 recurring, which is approximately 0.67 amperes as required. So we don't expect another circuit to give us the same answer. So the answer is A. The diagram shows a network of 3 resistors two of these marked R are identical. The other resistor has a resistance of 5 ohms. Okay. So the resistance between Y and Z is found to be 2.5 ohms. Resistance between Y and Z. That means this side is open. When this side is open, the resistance between Y and Z is found to be 2.5. That means if current flows from Y, it is going to be the same current there, same current there. So that means these two are in series. So total resistance, this side is going to be 2R plus R. And total and resistance this side is 5. So this combination, this side, is in parallel with that. So it's like having these resistors like this. So this is the 5 ohms. So this one, because the other one is X is open, so there is no problem there. We are considering these two important points, Y and Z. These ones are identical, R and R, 5 ohms. Total resistance is found to be 2.5 between Y and Z. That means, remember 2.5 is half of 5. That means these two resistors should be giving a combination of, should give a sum of 5 ohms. Alternatively, we can say since they're in parallel, 1 over parallel resistance is going to be 1 over the resistance in series here plus 1 over 5. So 1 over parallel resistance is going to be 1 over 2.5 is equal to 1 over resistance in series plus 1 over 5. So it means 1 over the resistance in series is going to be, I'll just press my calculator, open brackets, 1 divided by 2.5 minus, I take 1 over 5 the other side, 1 divided by 5. So it means this is equal to 1 over 5. So these two resistors, they form a total of 5 ohms. And since they're identical, each resistor must be having 2.5. So this is 2.5. This one is also 2.5 ohms. Okay, now we know their resistances. What is the resistance between X and Y? So now we are repeating this time, we are looking at X and Y. So it means R, this resistor here, and 5 ohms are going to be in series. So we shall have something like this. Let's have a resistor here of 2.5, that side. So this side we have X and we have Y somewhere there. So this side we have 5 ohms and we also have R, which is 2.5. So it means this part of Z is open. If we are finding between X and Y, this side of Z is going to be open. So Z is that side is open. So these two are going to be in series. So it means we have 5 and 2.5 are in series, giving us 7.5. Then the resultant is in parallel with 2.5. So total resistance, because we are going to consider a parallel combination. So resistance between X and Y is going to be 2.5 for this one. The sum of these two is 7.5. So this is times 7.5 divided by 2.5 plus 7.5. I'm just using product over sum for resistors in parallel. I'm saying these two are in series. When you combine them, they give you 7.5, which is in parallel with the 2.5. So note that very carefully. So let's check this with our calculator. So this is going to be 2.5 times 7.5 divide by, open another bracket, 2.5 plus 7.5. This is going to be 1.875. 1.875, that is 1.9. So our answer is going to be C. The diagram shows a battery, a fixed resistor, an ammeter, and a variable resistor connected in series. Okay. The resistance of the variable resistor is reduced. That is very beautiful. If resistance of the variable resistor is reduced, what happens to total current in the circuit? So total resistance, R total, becomes smaller. If total resistance becomes small, total current in the circuit actually increases. The total current in the circuit increases. What does that mean? The ammeter is connected in series with the battery. That means the ammeter reading must increase. So we cross out decreases. So the ammeter reading has increased. Okay. But then, I think there was negligible internal resistance. Okay. So if the circuit current, total current has increased, it means this is a fixed resistor. Now the current through it is higher. The current through it is now higher. So it means the PdV is going to be I times R. Even though this is fixed, current has increased, V has increased. So it means our answer is going to be D. The circuit diagram shows a battery of e.m.f. 9 volts and a negligible internal resistance. It is connected to two resistors of resistance 160 ohms and R. The output potential difference, V out, is 4 volts. So if this is 4 volts, you can even predict that if this is 4, the other one should be 5 because the sum should be 9. Okay, what is the resistance R? So we just use potential dividers. V out is going to be R over R total times V supplied times V in. Okay, so V out is 4, R is not known, R total will be R plus 160. So this is going to be multiplied by V in, that is times 9. But that one is a long method, but still it gives you the answer. Alternatively, I can say since I know this one is 5, I can still say 5 is equal to 160 over total resistance, which is 160 plus R times the voltage supply, which is 9 times 9. I'll get the same answer. But this one is shorter. The algebra here is shorter. You can even just press your calculator and say 160 plus R is equal to, on the other side you have 160 times 9 divided by 5, which is 288. 160 times 9 divided by 5, which is 288. Then it means R is 288 minus 160, which is 128. So the answer here is most likely going to be D. So R is 128. Alternatively, this could also give you, let's check it very fast. Cross multiplying, I have 4R plus 4 times 160, that is 640, is equal to 9R. So collecting like terms, you have 640 is equal to 5R. So you have 640 divided by 5, that is 128. In the circuit shown, XY is the length L of uniform resistance wire. A potential difference is applied across XY. R1 and R2 are unknown resistors. J is a sliding contact that joins the junction of R1 and R2 to points X on XY through a lamp S. J is moved along XY, point at which the lamp is off. Of course, when the lamp is off, there is balance. So the PD across R1 is going to be the PD across the length X. Remember, PD is directly proportional to the length. So it means V1, which is the PD across R1, is going to be a constant times X. Similarly, when we transfer this to this point here, J is moved along XY at a point at which the lamp is off. This point is at distance X from X. The potential difference across R1 is V1, and the potential difference across R2 is V2. So the potential difference across R2 is V2. But to find R2, we can now transfer this to this point here. We can transfer this to this point. We put our lamp somewhere here and we find a new balance length. And they have told us that if we put it at Y, then the length is going to be L. So we shall just say V1 plus V2 is going to give us a constant times L. So that means we can find V2. V2 is going to be KL minus V1, which V1 is K times X. In other words, V2 is going to be a constant into L minus X. Now let's see the ratio. The ratio is V1 over V2. So V1 is Kx over V2, which is K into L minus X. So this gives us X over L minus X. Therefore, our answer is D. I think I left out something about this question. XY is the length L of uniform resistance. The potential difference, okay, that is fine. There's nothing left out there. When there is a current of 5 amperes in a copper wire, the average drift velocity of free electrons is 8 times 10 power negative 4 meters per second. What is the average drift velocity in a different copper wire? So it is the same, it is still copper, so resistivity is the same. N is the same, E is the same, but with twice the diameter, that means the area is different. Remember, area is pi d squared divided by 4. Okay, so from current equals to never, this is going to be, so I'm going to come up with 3 equations. Remember, area is pi d squared. So for the first one, I have 5 is equal to NE. The drift velocity is given as 8 times 10 power negative 4. The area is going to be pi, let the diameter be d squared, then divide by 4. For the second wire, this is going to be 10. This is NE times the drift velocity is not known. I'll call it V2. Area is going to be pi. Where there is diameter, I'll put twice d. So this will be twice d, but is squared, then divide by 4. When I combine these 2 equations, either by dividing, of course, this one is going to give me 10 over 5 equals to NE V2 times pi times 4 d squared. There's a 4 down there, divide by NE, the velocity was 8 times 10 power negative 4 times pi times d squared over 4. A mathematician does not do all this, but I do this for most of us who are not really interested in math. So pi cancels, 4 that is cancelling, d squared is cancelling. So of course 5 by 10 by 5, that is 2, so 2 is equal to V2. Divide by, of course, by 4 here is 1, by 4 here it is 2. So divide by 2 times 10 power negative 4. And when you cross multiply, you notice that V2 is going to be 2 times. Is going to be 2 times that, which is 4 times 10 power negative 4. That means our answer is going to be A. What is equivalent? What is equivalent? What is equivalent to 1 volt? So 1 volt, volt is the unit of PD or EMF, which is work done per unit charge. Work done is in joules, charge is in coulombs. So a volt could be joules per coulomb. 1 joule per coulomb, so our answer is B. The diagram shows a rectangular block with dimensions x, 2x, 3x. Electrical contact can be made to the block between opposite pairs of faces, for example, between faces labeled R, that is on top and the bottom. Which statement describing the electrical resistance of the block is correct? I see all of them have maximum, and it is the same whichever pair of faces. It can't be the same because the length resistance is equal to rho L over cross-sectional area. So if we say between if the length is longer, then it means and if the length is longer, then the cross-sectional area is smaller. It means the resistance is going to be higher. So let's look at which pair. Which side, which pair has the longest length and the smallest cross-sectional area. So the longest length is going to be when the current is entering from this side and emerging from the other side. That's the longest cross-section, the longest length. And let's check the area. Is it having the smallest area? The area here is going to be x times 2x, which means the area this side is going to be 2x squared. The area here is also 2x squared. So the cross-section area of the other side is 2x squared. But then this side, it will be 3x times x, which is greater. The area for this side is 3x squared. For the top, it is 3x times 2x, which is going to be 6x squared. So this is the greatest area. It means you'd have smaller resistance for the same length. Therefore, our answer should have, when L is longer, area should be smallest, for the resistance should be the greatest. So maximum resistance will be between faces labeled Q. That's where we shall have maximum resistance. So it is maximum between the faces labeled Q, yes, because they have the smallest area and the length is greatest. Smallest area, the greatest length. A battery with internal resistance is connected to a parallel arrangement of two resistors and a switch, as shown here. Initially, switch S is open. What happens to the voltmeter and ammeter readings when switch S is closed? So when switch initially it is opened, so there's a voltmeter reading and an ammeter reading. When it is closed, so when it is closed, total resistance here becomes smaller, which means resistance in the circuit is going to decrease. If resistance in the circuit decreases, it means the current in the circuit increases. Total current in the circuit increases. That means the reading of the ammeter must increase. So ammeter reading, of course, we start with the ammeter reading, it must increase. So this one is wrong, that is wrong. We eliminate B and D. Then the voltmeter reading, let's see, there is an internal resistance. If the current in the battery increases, remember, terminal PD is equal to EMF minus the lost volts. This is equal to EMF, which does not change, is constant, minus current times internal resistance. Remember, current has increased, so the lost volts have increased, terminal PD decreases, which means the voltmeter reading must automatically decrease. Therefore, V voltmeter reading or terminal PD decreases because the lost volts increases. So the answer is going to be A. A battery is connected to a network of 6 resistors as shown here. The potential difference across 5 of the resistors are labeled on the diagram. What is the potential difference across resistor R? Okay. So we can use Kirchhoff's second law precisely. So we will put a loop here. I'll put a loop there, and I can also put a loop here. So the current, of course, when it comes here, I is divided into, say, I1 and I2. So here we have current I2. So if I choose a loop in this direction, for this side, the EMF is, for the left-hand side, okay, let's just look at this side here only. There is no battery here, so the EMF is 0. So let's look at the PDs. 3.7, 4.1 will be negative because they're in the opposite direction to the current which I've chosen. So this will be negative 4.1 minus, because they are the other way around. So this will be negative 4.1 minus 3.7. I'm moving, then for this one to be positive because the current is in that direction, so this will be plus 2.2. Then for this one to also be positive because the current is I1, so it will be plus 1.2. For this one to be positive, so it will be plus PD across R. So there's only one unknown, which is the PD across R. So I'll just pull out my calculator to be very careful. So I have negative 4.1 minus 3.7 plus 2.2 plus 1.2. That gives us negative 4.4. The negative just shows that I chose the wrong direction of the loop. So this is going to be 4.4 volts. So our answer is automatically going to be A. So if I had started with this loop, it would take me longer, but starting with the other loop has simplified my life. Again, I'm very sure people would wish to multiply the current with the PDs, yet already the PDs have been calculated. The reason as to why I put there the currents, just to tell you the direction when you are considering the signs of the PDs. The diagram shows a battery of e.m.f 6 volts connected in series with a resistor and a uniform resistance RQ of length 60 centimeters. The resistance of RQ is equal to the resistance of the resistor. So if this is the resistance here is the same as the resistance there, let's say it is RR. Let me use small r so that because capital R has been used already. So let's say this is small r, this is small r, that is the resistance. Terminal X is connected to a fixed point R, terminal Y is connected to point P, a connection that may be made at any position along the wire. L is the distance between R and P. Which graph shows the variation with L of the potential difference V across X, Y? L is the distance, so it is a graph of V against L. So remember, the total PD, the total EMF E is going to be the PD across the length L plus the PD across PQ plus the PD across the fixed resistor, which I'm calling small r, or simply PD across RQ plus the PD across the fixed resistor. So what happens to which graph shows the variation with the L of the potential difference V across X, Y? Of course, PD is directly proportional to length. PD is directly proportional to length. We expect a straight line. Okay. When we bring X, when we bring y to that point, p to that point, that means the PD across xy is going to be 0 because there will be no length. So the graph should start from 0. So we eliminate those ones which are not starting from 0. When L is 0, V should be 0. So this is wrong, that is wrong. So we remain with these two. But then, what happens when L is equal to Q? I mean, when L is equal to RQ, it means now the length, remember the resistance RQ is the same as this. So it means the 6 volts is going to be divided equally because now the total resistance here is the same as that one. So the 6 volts is going to be divided equally because the PD across RQ will be equal to the PD across the fixed resistor. And since the total should be 6 volts, so the PD across RQ plus the PD across the fixed resistor should give us 6, which means when P is at Q, the PD across RQ is half of 6, which is 3 volts. This one is also 3 volts to give us a total of 6. Therefore, our correct answer is going to be B. It can't be A because A is showing that when we reach Q, when L is equal to 60 centimeters, which is at point Q, it is showing that the PD is actually going to be the same as the e.m.f. That means the PD across the fixed resistor would be 0, which is practically not possible. Therefore, the answer is B because B is showing when L is equal to 60, the PD is almost half of 6, which is 3. So the answer is going to be B. Which two units are used to define the coulomb? Remember, coulomb is charge equals to I times T. That is coulomb, that is ampere, that is seconds. So it is going to be ampere and seconds, that is A. An electrical device is fixed. An electrical device of fixed resistance 20 ohms is connected in series with a variable resistor and a battery of e.m.f 16 volts and negligible internal resistance. What is the resistance of the variable resistor when the power dissipated in the electrical device is 4 watts? Okay, I think that is very easy, although it could be a long process, but let's try out. So we know that power is equal to I squared R. So the power in the device is 4. We are trying to find the current is I squared, then times the resistance of the device, which is 20. So the current through the device is going to be the square root of 4 over 20, which is root of 4 over 20. So that is 0.447. 0.447 amperes. That is the current. It is, of course, the same current here. It is the same current there. We can find a PD across the device also. PD across the device is going to be, PD across the device is going to be current in the device times the resistance of the device. So it is going to be 0.447 times 20. So I'll just say times 20, which is 8.94. So this is 8.94 volts, which means if this is 8.94 volts, this means this will be 16 minus that. So 16 minus the answer is 7.06. So the PD here is going to be 7.06. PD across the variable resistor is 16 minus 8.94, which is going to be 7.06 volts. Now it is easy because the current is the same. We can find the resistance. By Ohm's law, resistance is equal to V over the current. 7.06 divided by the current, which is 0.447. So divide by 0.447, which is equal to 15.78. That is approximately 16. So this is approximately 16 ohms. So the answer is A. A wire of length L has a resistance R. The cross-sectional area of the wire is circular with a radius R. A second wire, also of circular cross-section and of the same material, that means the resistivity is the same, has a resistance a half R. What could be the radius and the length of the second wire? Okay, let's begin with the area. Of course, we know that area is going to be pi r squared. They give us the radius, so the area is going to be pi r squared. And we know that resistance is going to be rho L over cross-section area. So it means this is going to be rho L over pi r squared. So let's have these two equations. For the first wire, I'm simply going to make resistivity the subject. You can do it in any way, but this is, to me, this is going to be the easiest. So I make resistivity the subject. Resistivity is going to be R times the area divided by L, which will be resistance times pi r squared divided by the length L. So this is for the first wire. Let's look for the second wire. Because it's the same material, resistivity is the same. Resistance is half R. So where there is R, I'll put a half R times pi. Then the second wire also of circular cross section and same material has resistance R. So we don't know its radius. So I'll call it R2 squared. Divide by what could be the radius and length. So we even don't know its length. I'll call it L2. Okay. So I'm going to simplify this further. Note that R and pi are going to be constants. What is going to change is small r and L. So here I'm going to have this as R pi into R squared over L. So here, this is going to be equal to R times pi over, that is R times pi into brackets, I will have R2 squared divided by 2L, 2L2. Okay. So we are going to look for a combination. We are going to look for a combination. We are going to check all these combinations and see which combinations of R2 over 2L2 will give us this part here, R squared over L. So you check. When I'm going to check the first and the last only, because they are the ones which are most likely making sense to me. So when R2 is equal to R over 2, and then L2 is equal to L over 2, we check this part here only. Does it give us R squared over L? Because if it doesn't, then rho is not constant. So we substitute it there. So we have R2 squared over 2L2 is going to be R over 2, this is squared, divided by L. L2 is going to be twice 2 times L over 2. So this one cancels. So you remain with R squared divided by 4L. So this one does not give us that. So that will not work. So A is wrong. Let me check the last one, D. I'm going to just put the values, the pairs given into that expression there to see if it takes me back to that. So this is going to be R2 is going to be twice R divided by L2. So this will be 2 times, by the way, remember this is squared. So this is twice R squared, and in the denominator we have 2L. So it is 2 into 2L. So this is giving us 4R squared over 4L, which gives us R squared over L. So this takes us back to It is taking us back to that. That means this combination will give us the constant resistivity, so the answer is going to be D. It's quite technical, but for mathematicians, they could find another way of coming up with that answer. A battery of e.m.f of negligible internal resistance may be connected between any 2 points P, Q, R, and S of the network of resistors shown. Which connections will give the largest current and the smallest current in the battery? For largest current, resistance should be smallest. For smallest current, resistance should be greatest. Now we first of all look at these resistors. Which one is the smallest? Is 3. Therefore, if we connect a voltmeter across PQ, it means the total resistance will be less than 3, because these will be in series, and then the combination of these will be in parallel with 3, which will make the resistance to be smaller than 3, because resistors joined in parallel will form a small resistance than when resistors are in parallel, the total resistance is less than the resistance of the smallest resistor there for parallel connection. So we shall put the voltmeter across the smallest resistance, meaning that the others will be in a series. We combine them, this will be 6, 10, 15. So 15 is going to be in parallel with the 3 ohms, so that when we find total resistance, it is smaller. And if total resistance is smaller, then it means the current is greatest. So current is the greatest when we connect, when we make which connections will give the largest current and the smallest current in the battery. So current is going to be greatest when we connect across P and Q. So we eliminate RS, that is C and D. Then for the smallest current, the resistance must be greatest. And we have options. We have the easiest option would be, I will use a different color for the same diagram. The easiest option would be to connect across S and Q here. The easiest connection will be between Q and S. Why? It means 6 and 3 will give us 9, 4 and 5 will give us 9. These 9 and 9 will be in parallel. Total resistance in parallel, remember total resistance in parallel will be half of that, which will be 4.5. In other words, is 9 times 9 over 9 plus 9, which is 4.5 ohms. That will be the greatest resistance, which will give us the smallest current. Somebody will say, why can't we connect across P and R? Let's see if you had chosen P across PR. If you had put your connections between P and R here, if you had put connections between P and R, it means 3 and 5 are in series, so that gives us 8. 6 and 4 in series, that gives us 10. Now this 8 ohms and the 10 ohms are in parallel. Let's find total resistance. Their total resistance, 1 over total is going to be 1 over 10 plus 1 over 8. I'm very certain this value is less than 4.5. So LCM, if we say the LCM is 80, so 80 gives us 8 plus 10. So it means total resistance is going to be 80 divided by 18. So let's check 80 divided by 18. That is 4.4 recurring. So this is 4.444 recurring, which means this resistance, when you choose these connections, the resistance is less than 4.5. So the greatest resistance is 4.5 when the connection is between Q and S, which makes 5 and 4 in series, 6 and 3 in series. Then the combination gives us 9 and 9, which are in parallel, giving us total resistance of 4.5. Therefore, our answer is going to be B. Kirchhoff's second law is a consequence of a basic principle. Second law is energy. So without any hesitation, it is the energy in an electric circuit is conserved. That is very simple. Two cells are investigated using a potentiometer. At the balance point, cell X gives a reading 44 centimeters, cell Y gives a reading 70 centimeters at balance point. Note that balance is only obtained when the e.m.f of these cells is less than 6 or is less than the driver cell. Normally the e.m.f of the cells must be less than the e.m.f of the driving cell. That's number one. Number two, the positive terminals must be linked if balance is to be achieved. If it is not, then it is not possible. The PD across this balance length is the same as the EMF of the cell. Let's see the question now. Which statement is not correct? A potentiometer balance point results in zero current through the galvanometer. That is true. If there is balance, the current through the galvanometer is zero. The resultant is zero. At balance point, the current through resistor R in both circuits is the same. At balance, yes, because the current through the galvanometer is zero, then it means the current through R both will be the same at balance point. So that is also true. Then the EMF of the cell X is larger. That cannot be true. The EMF of this cell X, is it larger than Y? The EMF of cell X is larger than the EMF of cell Y. That is not true. Reason: the EMF is the same as the PD across the balance length. PD across the balance length. And the PD is directly proportional to length. The balance length for Y is greater than the balance length for X. Therefore, the EMF of cell Y is expected to be greater than the EMF of cell X. So it means this statement C is not correct. The value of the EMF of each of the cells X and Y is less. That one is supposed to be true. The current I in a copper wire can be calculated using the equation. What does the symbol V represent? That is average drift velocity. So the answer is A. Three resistors are to be connected into a circuit with the arrangement shown. The power in any resistor must not be greater than 4 watts. The power in any must not be greater than 4 watts. So if we have this resistor in series, we can find its power. So we know that power is equal to, okay, the power across this one is it should not go beyond 4. Since we know the resistance, we can find its speed. So power is equal to V squared over R, which means that PD across that one, which is outside, I'm going to call this one V1, and the PD here I will call it V2, because here it is the same. Maximum voltage will be V1 plus V2. So V1 is going to be equal to the square root of P times R, which is equal to the square root of P should not go beyond 4 and R is 100. I think this is the square root of 400, which is 20. That is 20 volts. So that is the PD across 100. Then let's try to find the PD across this one here. Now I want you to note that when we have these two in series, in parallel, their total resistance is 50 ohms. 100 and 100, that is 100 times 100 divided by 100 plus 100, that is product of a sum for parallel combination. This gives us 50 ohms here. So here it is 50, which is half. And if we have a resistor, a circuit which is like this, where this is 50 ohms and this is 100 ohms, of course the current through them is the same. So from power equals to I times V. If the current is the same, or let me say power is equal to I squared times R. If the current is the same but the resistance is half, it means the power is also half. So the power here is half. So the power there is going to be 2 watts. So again, I'll use the same formula, V. So I will say power in the parallel combination is going to be a half of 4, which is going to be 2 watts. So using V equals to the square root of power times R, so this will be V2. V2 will be the square root of the power, which is 2, times the resistance, which is 50. And that is root over 100, which is 10 volts. So to find total voltage or the maximum voltage between X and Y, we shall add 10 plus 20, which gives us 30 volts. So our answer is B. Gold is sometimes used to make very small connecting wires in electronic circuits. A particular gold wire has length of 2.5 times 10 power negative 3 meters and cross-sectional area 6.25 times 10 power negative 8 meters. Gold has resistivity of 2.3 times 10 power negative 8 ohm meters. What is the resistance? So this is direct. We have resistance is equal to rho L over area. They gave us area, they gave us resistivity, they gave us length. So this is going to be 2.3 times 10 power negative 8. Length 2.5 times 10 power negative 3. Cross-sectional area 6.25 times 10 power negative 8. So we have this as 2.3 exponent negative 8 times, even if I don't put multiplication there, 2.5 exponent negative 3 divided by 6.25 exponent negative 8. So that is giving us 9.2 times 10 power negative 4 ohms. Okay, so the answer is going to be C. A resistor X of resistance 40 ohms and variable resistor are connected to a battery of EMF 12 volts and internal resistance 2 ohms. The resistance of the variable resistor is changed from 0 to 40 ohms. What is the change in power? Let's assume this is at 0. So what is the power here? So we note very well that if it is at 0, V is equal to I, or current is equal to EMF over total resistance. So EMF is 12. Total resistance will be 0 plus 40 plus 2, which is just 42. So that is the current. Then we know that power, I will call it power 1, is going to be equal to I squared times R, which is going to be equal to 12 divided by 42, and this is squared, times R, which R is, remember we are finding power across X, so that is times 40. So we can press the calculator here. 12 divided by 42 squared times 40. So that is approximately 3.27. So the second power, power 2, is going to be, of course, here the current again changes. So if we consider it at 40, so the current is going to be the EMF 12 divided by 40 plus 40 plus 2, which is 82 amperes. So the power 2 is going to be I squared, which is 12 over 82. 12 over 82 squared times 40. So we have 12 divided by 82 squared times 40. This gives us 0.8, 0.8. I want two decimal places, so this is going to be 0.887, 0.86 watts. So let's find the change in power. The change in power is going to be the difference, 3.27 minus 0.86. So 3.27 minus 0.86, that is approximately 2.4. So this is 2.4 watts, which is A. All the resistors shown in the resistor network W, X, Y, and Z have the same resistance. Which list gives the network in order of increasing total resistance? Okay, so you and me will notice that this one should be having the highest, because this one is, if we say R, 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 so this is 2R, this is R over 2 plus R. R over 2 plus R is 1.5 R. That is the total resistance here. R plus R over 2 is 1.5 R. This is R and this is R. If they are in parallel, it is R times R over R plus R, which is 0.5 R. Then here these two are in series, so this is 2R plus, and this is R. So the product over the sum, you have 2R times R over 2R plus R, which gives us 2R over 3, which is 0.67 R. Then we check this one. This is R plus R, that is 2R, R plus R, that is 2R, but they're in parallel, so we have 2R times 2R over 2R plus 2R, which is 4R squared over 4R, which gives us R. So this is number 1, the highest, and I think this is going to be number 2, this is number 3, and this is number 4, the lowest. So we want in order of increasing total resistance. So the smallest is X, so X comes first. The highest is W, W comes last, so that is D. In the circuit shown, the ammeter reading is 0. Of course, if the ammeter reading is 0, it means no current is flowing through the ammeter. There is balance. Of course, even here there is no current. So that means the potential difference across this is the same as the potential difference there. So let's first find the PD across 100. So the PD across 100 is going to be V equals to resistance, which is going to be 100, divided by total resistance, which is 150 times 12. So you have 100 divided by 150 times 12, that is 8. So this is 8 volts. So the PD here is 8 volts. This is 4 volts because the total should be 12. But if there is balance, there is no resultant current through the ammeter, it means the potential across 100 is the same as the potential across this 200. So here it is going to be 80 volts. And if this is 80 volts, remember the cell which is connected is of 24 volts. So I can find the PD across this one. So PD across capital R is going to be 24 minus 8, which is going to be, I think that is 16 volts. So the PD across that one is 16 volts. What is the resistance of resistor R? What is the resistance of resistor R? So let's first find the current. If the PD across 200 ohms is 80 volts, so the current there is going to be 8 divided by 200. That is the current here. It is the same current through R. So it means the resistance R is going to be V over the current. V is 16, the current is 8 over 200. So 200 goes up, I will say 200 times 16 divided by 8, which is 400. So R is equal to 400. So the answer is going to be C. An electric current in I is given in the list of the formula on page 3 as I is equal to A N V Q, so we know that one. What do each of the symbols represent for an electric current in the ammeter? A is cross-sectional area, so this one is wrong. V is average drift speed. V is average drift speed, is not voltage. So this one is wrong. So we're remaining with only B. So the answer is B. Without wasting time, of course, Q is charge, average drift speed, number of free electrons, area of cross section. The potential difference across a resistor is 12 volts. The current in the resistor is 2 amperes. A charge of 4 coulombs passes through the resistor. What is the energy transferred in the resistor and the time taken for the charge to pass through the resistor? So let's begin with the energy. We know P is energy over charge, so it means energy is going to be the charge times V, which is going to be 4 times 12, and that is, I think, 48 joules. So we eliminate these two. A is out, B is out. So let's check the time. We also know that energy is equal to power times time, which is equal to IV times time. So it means 48 is going to be I, which is 12, which is 2, times V, which is 12, then times T. So T is 48 divided by 24, which gives us 2. So our answer is going to be C. A coil contains n turns of insulated copper wire wound onto a cylindrical iron core of diameter D. So the diameter is D. So the coil contains n turns of insulated copper wire wound on the cylinder. So D is the diameter of the cylinder, it is not the diameter of the copper wire. Let's say the diameter of the copper wire is small letter d. Oh, it is even mentioned here. The diameter D is much greater than the diameter small d. The diameter of the copper wire is D. The resistivity is rho. What is the total resistance between the two ends of the coil? Okay, let's of course, since we know that the area is pi d squared, area is pi d squared over 4. That is for the wire, the cross-sectional area of the wire using small d. And then for the cylinder, let's assume this is the cylinder. And the wire is wound around the cylinder just, so it means the circumference of the wire which is wound around the cylinder is going to be got from the diameter of the cylinder. So perimeter or circumference is going to be equal to pi times d. The length of the wire which is made which makes one turn around the cylinder is pi d. So the length for one turn, L for one turn, is equal to pi d. Because remember, resistance is equal to rho times L over cross-sectional area. So length for one turn is pi d, but there are n turns. So total length L is going to be n times pi times d. That is the total length. Okay? So since resistance is equal to rho L over area, this is the same as rho L over the area, which is pi d squared over 4. The 4 goes up. So now I have that resistance is going to be 4. Resistivity is rho. The length is n pi d. I divide this by the area, or this is over pi d squared. So this is over pi d squared. So pi cancels out, and I remain with the 4 rho n d divided by d squared. So my answer is precisely going to be A, 4 n rho d over d squared. Two cells are connected to a load resistor of resistance 3 ohms. The EMF and internal resistance of each of the cells is shown. What is the current in the load? So that is very easy. I just draw in one loop, which is anti-clockwise. Sum of EMFs is 6 plus 3, that is 9. Sum of PDs, this is 3. Of course, the current is the same, so I'll say I into 3 plus 1.2 plus 0.8. So it means I is going to be 9 divided by, that is 2, and 3, that is 5. 9 over 5. So 9 divided by 5, which is 1.8. So this is 1.8 amperes. So the answer is C. 6 resistors, each of resistance R, are connected as shown. The combined resistance is 66 kilo ohms. What is the value of R? So this is R. If this is R and this is R, the total here is going to be R over 2 because they're in parallel. This is R, this is R, this is R. So 1 over R plus 1 over R plus 1 over R, because they're in parallel. The total here is going to be R over 3. Then we sum up R plus R over 2 plus R over 3 should give us 66. Because they're in series, the combinations are in series. This is in series with this, is in series with that combination. So LCM here I think is 6. So I'll say 6. So I have 6R plus 3R plus 2R should give us 66. So that is 11, I think. 11R over 6 is equal to 66. So I think R is equal to, is it 36? Because by 6, so this is 11, that is 1, that is 6. So R is equal to 36. You can check with the calculator. 66 times 6 divided by 11, that is 36 kilo ohms. So the answer will be D. A potential divider consists of two resistors of resistances R1 and R2 connected in series across a source of PDV in. Which changes to R1 and R2 will increase the value of V out? Which changes to R1 and R2 will increase the value of V out? So let's look at V out here. Using the potential divider formula, V out is going to be R1 over total resistance, which is R1 plus R2, times V in. Of course, V in is constant. This one is, change the color. V in is constant. So we want the change that will increase V out. Automatically, R1 must increase. R1 must increase. Already R1 should increase, so it is, we can't say halved, it must be doubled. And note that V out is inversely proportional to R1 plus R2. So it means R1 plus R2 should automatically decrease. But remember, R1 has increased. If R1 has increased already, it means R2 should decrease in order to make R1 plus R2 to be smaller. So R2 should decrease. Therefore, R2 should be halved. So it means R1 can be doubled and R2 can be halved. So our answer is going to be part to be B. R1 can be doubled because if I want V out to be greater, R1 should be higher. But then the denominator should be smaller. The only way I can make the denominator smaller, yet I've already increased R1, is by making R2 very small. Therefore, R2 decreases or it is halved and R1 can be doubled. Okay, let part 4 stop there. We shall meet in part 5. Have a blessed day. I hope you learned something. For any errors, I might have made a mistake. Anywhere, it is also possible, but is very rare. Or I might have not explained something to your expectation. You can always inbox me. You can write a comment. I have no problem with your comments. All the best. Bye-bye.